Hello everyone. In this video, I am going to discuss about the black body radiation and classical approach and quantum solution to explain the black body emission spectra. As we know that hot objects emit visible light, cool objects emit almost zero visible light. Heat is transfer of kinetic energy. There is no translational motion in solid, but there is vibrational motion. Here, when you take in the object, if it is heated, the electrons are vibrated and the vibrational energy is released in the form of electromagnetic radiation in the form of light. Coming to the black body, every object is not considered as black body. In nature, there is no perfect black body. That's what black body is considered as a theoretical or hypothetical object. Black body has the ability of absorb all kinds of wavelength incident on it, and it is perfect emitter of radiation over all the wavelengths. In case of black body, it has zero reflection and zero transmission because there is no reflection at all the wavelength radiation absorbed by the black body. That's why treated as perfect emitter, perfect absorber. Generally at absolute zero temperature, it is ready to absorb the radiation, but at higher temperature, it is ready to emit all the wavelength of the radiation. Kirchhoff first or initially proposed the concept of black body in the year of 1860. According to the Kirchhoff, a black body allows all incident radiation to pass into it and internally absorb all the incident radiation, and it is true for radiation for all the wavelength and for all angles of incidence. When you observe the emission or the radiation spectra of a black body at a particular temperature, when you take in a diagram between the wavelength is taken as x-axis parameter, and flux that also take it as y-axis parameter is energy density. If you draw the curve between the energy density versus wavelength, we observe the spectra is like this. This spectra is for a particular material when it is heated at 4000, when you given the heat treatment 4000 Kelvin, 6000 Kelvin, 18,000 Kelvin. So by seeing this diagram, we can understand that there are few points we can notice. One is at lower wavelength and at higher wavelength, the energy density or the flux value is lower. The energy density of the flux is increases with respect to the wavelength, and it's showing maximum for a particular wavelength, and then it is decreases. This is the first observation. And the second one, as the temperature increases, it's 4000 Kelvin, it is a 6000 Kelvin, and it is 18,000 Kelvin. As the temperature increases, the energy density value spectra, the energy density for each and every wavelength is increases. For example, when you see the red and blue curve, whatever the wavelength you consider from the lower to the higher, blue curve is above the red curve. That means energy flux, higher temperature object is more compared to the lower temperature object. This is the second observation. And coming to the third observation, the maxima corresponding wavelength For example, if I take in this is a T1 and is a T2 and it is the T3. Then obviously we can observe that T1 is 4000, T2 is 6000, T3 is 18,000. When you take in the T1, T2, T3, T3 is greater than T2, T2 is greater than T1. But wavelength point of view, lambda 3 is lower than the lambda 2 and lambda 2 is lower than the lambda 1. Then we can observe there is an inverse relation between the maxima corresponding wavelength and the temperature. With increasing the temperature, the wavelength shifts towards the lower side. That is also called as blue shift. This is the third observation. If you measure this kind of, if you draw this kind of spectrum for different kinds of material by giving the same temperature, there is no difference observed. There is no difference observed in the trend of the spectrum for the same temperature for different materials also. Then we can conclude that the black body radiation spectrum, it doesn't depend on the material what we chosen for the testing point of view. It completely depends on the temperature. It doesn't depend on the material selected for the experiment. For example, when you take in the iron material or the charcoal or the ceramic, if you given the same temperature, we can observe the spectra is also similar. So these are the observations from this diagram. The first point, that is the black body spectrum depends only on the temperature of the object and not on what is made of. Iron horseshoe, a ceramic vase, a piece of charcoal all emit the same black body spectrum if their temperatures are the same. And coming to the second observation, by seeing that diagram, as the temperature of an object increases, it emits more black body energy at all wavelength, energy density more for the higher temperature objects compared to the lower temperature object. As the temperature of an object increases, the peak wavelength of the black body spectrum becomes shorter, that is a blue shift. For example, blue stars are hotter than red stars. This is simple logic. And there is an inverse relation between the maxima corresponding wavelength and the temperature. This is the relation, that is lambda m and T is always constant. It is proposed by Wiens. Coming to the last one, the black body spectrum is always become small at the left hand side. The shorter wavelength, higher frequency side, we observed that the spectra is always lower. To explain this observed spectra, initially classical approach is like this. According to the classical theory, light is an electromagnetic wave emitted when an electric charge vibrates. Initially, when electric charge vibrates, electromagnetic radiation is emitted. Depends upon the vibrational frequency, the energy is different. In the case of hot object, electron vibrate in random direction and produce light as a result. Hotter object, that is when you keep on increasing the temperature, more energetic vibrations, and so more light is emitted by a hotter object. It glows brighter. So classical physics successfully explains that with respect to the temperature, for example, when you take in the, this is a lower temperature and it is the higher temperature, so he can able to successfully explains that hotter object, like if it is higher temperature T2 and it is T1, in case of classical mechanics, obviously at higher temperature, more energetic vibrations, then more light is emitted, then it glows brighter. Energy density for the hotter object is more compared to the low temperature object. And coming to the classical approach, especially for the frequency related, the electrons in a hot object can vibrate with all range of frequencies from the lowest to the highest, and there is no limit to how great the frequency may go up to infinity also. And if infinite frequency vibrated body can release the infinite amount of energy. So similarly, the classical physics, energy of light emitted by electrons vibrating at higher frequencies has no limit. Then obviously we are expecting that when you take in, this is the diagram, energy density flux on the y-axis, if you take in frequency on the x-axis, or for example, don't clarity point of view, taken wavelength, because already we draw the diagram with respect to the wavelength, right? So wavelength is lower, that nothing but frequency is higher. As the frequency more, energy density should be more. According to the classical physics, energy density should be more, and it keep on decreases with respect to the frequency decrement. The wavelength point of view, lower wavelength, the energy density expectation is more. This is the classical approach. But in reality, the diagram is not like this. So here, just see this difference. This is the classical approach. So when the frequency is higher, it should emit more radiation, and radiation density should be decreases with respect to the frequency decrement. This is the observed classical approach, classical mechanics approach, and it is proposed by Rayleigh's criteria. But when you take in the real-time observation point of view, this is the reality. Observation is not at all matched with the classical approach. So we can conclude that classical theory, or the logic behind the classical, is not significant in explaining the reality of a black body emission spectra. So obviously the outcome of the classical mechanics completely contradict the experiment, and this contradiction also completely reverse. It is even worse theory to explain the observation, especially for the higher frequency side. As the lambda approaches to 0, we are expecting the infinite energy, but here it is the lowest energy. The difference approach in the higher frequency side between the classical to the observation spectra is called as ultraviolet catastrophe, and it is first used by Enfrost in the year of 1911. Coming to the the quantum solution to overcome this ultraviolet catastrophe. So according to the classical physics, we feel that energy is continuous. To remove the ultraviolet catastrophe in the black body explanation, Planck proposed that the vibrational energies of the atoms are quantized. That is, vibrating atoms can only possess certain discrete amount of energies. So the vibrating body can able to release the energy either in the form of photon like h nu, 2h nu, or 3h nu, or nh nu. So here n is the number and h is the Planck's constant, nu is the vibration frequency. For example, if the body is vibrating with the frequency nu, and it could only have the energy either 1h nu, 2h nu, or 3h nu, or the 4h nu, or nh nu. So there is no continuous energy according to the Planck's. But how Planck's or like assumption can able to explain this complete spectra of the black body that I am giving here? When you take in, the energy density value is lower for the high frequency side as well as low frequency side. And coming to the most important point according to the Planck's, if the vibrating body or the vibrating electron is to radiate, it must have at least one quantum of energy h nu. It will not emit light until and otherwise if it has at least energy 1 h nu or hf of energy. But what about the higher frequency point of view? At higher frequencies, so we have to consider h into nu, right? If it is higher frequency nu, then the quantum of energy en, each quantum energy is very high. each quantum energy is very high. If the particle or the electron doesn't have that much energy, it's impossible to radiate energy. So at the same time, within the black body, no electron has that much frequency. No electron is not vibrating with high frequency. Then obviously there is no much energy is liberated at high frequency side. That's what the at higher frequencies the energy density value is lower. So here just see this, at higher frequencies the amount of energy in a quantum h nu is so large that the high frequency vibration can never get going. That is why the black body spectrum always becomes small at the left hand side. In this way, Planck can able to explain the complete black body radiation spectra from lower end of frequency to the higher end frequency point of view. Coming to the summary, the black body radiation curve have quite complex shape. So it's not following any specific formula, just it's showing like a different trend. That's what called as complex shape. The spectral profile at a specific temperature corresponds to a specific peak wavelength and vice versa. The relation between the peak wavelength and temperature is Wien's law, that is lambda into T is always constant. That is, if the temperature is more, the peak corresponding wavelength shifts to lower side. For example, when you take in this, so this is the shift in the peak. The intensity at all wavelength increases as the temperature of the black body increases. For example, when you take in this upper curve is take it as T2 and down curve is take it as T1, and I assume that T2 is greater than T1. For any kind of wavelength, the energy density is more. The total energy being radiated increases rapidly as the temperature increases. So the area under the curve is representing the energy density at a particular temperature. That is given by the Stefan-Boltzmann law. That formula is E equivalents to sigma into T power 4. Although the intensity may vary low at a very short or the longer wavelength, at any temperature above absolute zero energy is ready to emit radiation at all wavelength. That means the black body curve never reach to the x-axis, because above absolute zero every body is ready to vibrate little amount of energy. So this is a summary related to the black body. Thank you very much.